Good morning, Internet. I am Matt Buyak, and in this video, we'll be taking a look at the 51st problem from the Project Euler Problem Archive. Now, this problem asks a question about families of primes, and it describes a family of primes as a set of primes which can be formed by starting with a particular prime and picking a particular digit which appears in that prime, and replacing it with everywhere it appears in that prime with other digits to form other primes. And those other primes, together with the original prime, comprise the family. It gives examples of the smallest prime, which is a member of a 6' family, and the smallest prime, which is a member of a 7' family. And it asks us to find the smallest prime, which is a member of an 8' family. Now, the first question that jumped into my mind when I read this problem description is, are we allowed to modify the leading zeros? That is, this number 13 could be written as 1-3, or it could be written as 0-1-3, or 0-0-1-3, or 0-0-0-1-3, etc. And I was wondering, are we allowed to replace those zeros with some non-zero digit? It's actually equivalent to ask, are we allowed to replace the most significant digit in a number with 0, thereby creating a shorter number? And it appears that the answer is no. Consider if we took 13 in this family here and replaced 1 with 0. You'll notice that this family was created by replacing 1 with 2, 4, 5, 7, and 8. And if we were to replace 1 with 0, that gives us 3, which is also prime. And so that would seem to be creating a 7' family, including 3. But we're told that this is the smallest prime, which is a member of a 7' family. And so that suggests that we are not allowed to replace the most significant digit with a 0. Other than that, our solution should be fairly straightforward. We'll just consider each of the primes in order, and for each one, we'll consider the digits 0 through 9, which may appear in that prime, and we'll consider all the all the digits we might replace that digit with, and see which numbers created in that way are prime. And once we find a prime that is a member of an 8' family, we will have our solution. So let's get to writing some code. As usual, we will copy our template directory to make our problem directory, enter our problem directory, and open our main.cpp. We will need to include primes.h because we will be doing some work with primes. We will need to link in our number theory library, which has the primes class in it. Okay, and so here we'll need an instance of our primes class, call it P. And then we will want to iterate over the index of our prime, call it I, from 0 up to infinity, incrementing by 1. We actually can delete these last 2 lines because we're never going to exit this loop. As soon as we find our answer, we'll just return directly. And we can say int n is equal to p.getPrime I. So that's going to get the ith prime for us. Okay, so now we want to consider all of the digits that we might use as our find digit. So we're going to find a digit and then replace it with some other digit. And so let's say for character C, just C, equal to 0, c is less than or equal to 9, and increment c. And for a given starting digit, we want to count the number of replacements we can make, which will give us another prime. And so let's say int count equals 0. And now we're going to try our possible replacements. So we'll say for char d is equal to 0, d is less than or equal to 9 plus d. But we have to be careful. We don't want to replace a digit that's, or we don't want c and d to be the same, because that won't actually give us a new number. Another point of caution, this should actually be 1, because we're already starting with 1 prime. Okay, so here we'll say if c is equal to d, we're just going to continue. Don't even consider that case. Okay, so now we need to apply our find and replace operation. And the way we're going to do that is to convert our prime to a string and use this function here, which basically does exactly what we want. We're going to need to include algorithm in order to use that. And we'll also need to include string. Okay, so let's go down here and we'll say std string equals std toString n. So that's convert our integer to a string. And then we'll do std replace. We didn't actually give our string a name. That would be important. So str.begin, str.end. This is just saying that we're doing the find and replace over the whole length of the string. And we're going to replace c with d. Okay. So now we need to convert our modified string back into an integer so we can check if it's prime or not. So we'll just say int result is equal to s to I of str, and then we'll say if p dot is prime result, and result is not equal to n. And I'll get back to that in just a moment. Then we're going to say plus plus count. Okay, so why do we have to include this check here, result not equal to n? Well, if we should happen to pick a digit for c that doesn't appear in our number at all, obviously this operation is going to have no effect. And we don't want to count our original prime again just because the find and replace had no effect. Already, you might be getting some sense that there's some room for optimization here. We'll get to that in just a minute. Okay, so after we've tried all of the possible replacements, we're going to say if count is greater than or equal to 8, printf, and we're going to say solution equals %d, it's going to be n, and then return 0. Now, there is one more thing we have to take care of before we test this solution. You'll recall me saying we have to be careful not to replace the most significant digit with 0. And so we have to figure out what the most significant digit is and then specifically disallow that replacement. So let's write a little helper function to do that. We'll say char get msd int n. So this is going to get the most significant digit, or the leftmost non-zero digit of our number n. So we'll say while n is greater than or equal to 10, n divide equals 10. And then we'll just say return n, actually let's convert that into a character, n plus 0. So after we divide off all the other digits, we'll be left with some value from 1 to 9. And then we can just add that to the character code for 0 to get the character code for some digit 1 through 9. Okay, so now we want to, at this point here, say char msd equals get msd. And at this point, we want to check to make sure that we are not replacing the most significant digit with 0. So we'll say d is not equal to 0, or c is not equal to msd. Okay, I believe that should be correct. So let's go back to the shell and make and run. We're going to time it because, as I mentioned, we're going to be making some improvements. Okay, so that came up with the wrong answer. I'm guessing that I made some mistake with this logic here. Let's see. So, oh, this should be an or. And now we're not finishing, so that's a little bit unfortunate. Let's go back again. So if we're making a no-op replacement, that is no good. And we also don't want to be replacing the most significant digit with 0. So if no, I have this backwards. It's if d, I took the negation for some reason. Here we go. Yeah, so if the case where we do want to skip is if our target or destination digit is 0 and our starting digit is the most significant digit. Here we go. Okay, so that looks better. Spoiler alert, I already know what the answer is supposed to be. Okay, so it took about 1/3 of a second for our program to finish. Not awful, but not great. Let's see if we can come up with some optimizations. So the first one, which I hinted at earlier, is down here. We're checking to make sure that our replacement even did anything at all, which is a big red flag that there's some room for optimization here. We don't really want to be trying all possible digits 0 through 9. We really only want to be trying the digits that actually appear in our number n. And so we want to somehow get the set of digits that appear in our number and only iterate over those instead. And we'll do that first by converting our number to a string. So we'll say std string digits is equal to std to string n. And then we're going to sort our digits in ascending order. So we'll say std sort digits dot begin digits dot end. Okay, and now we want to eliminate duplicates. This is a very common technique if you want to get a list of the unique items in your set. Sort it, eliminate duplicates, now you have the unique items that are in your set. And there is a method, stdUnique, which seems to do exactly this. We can say digits.begin, digits.end. But this function doesn't quite behave how you might expect. Let's go over to the documentation and take a careful look at it. So most of this description is exactly what you would expect. It goes through and replaces or eliminates duplicate items in your container. But what it doesn't do is erase the duplicate items. It just moves all of the unique items to be at the front of your container. And then it gives you an iterator. It says returns a past the end iterator for a new logical end of the range. What does that mean? Well, the normal end iterator for a container doesn't point to the last item. It points to just past the last item. That makes it easy to iterate over the whole container, because you can say, while your iterator is not the end iterator, keep going. That way you'll iterate over all the items, not just all but the last item. So a past the end iterator just means that it's similar to the regular end iterator in that it doesn't point to the last item, it points to one past the last item. But what does it mean by this new logical end of the range? Well, basically that just means that it's not pointing to the end of the container, it's pointing to the item one past the last unique item. And so we can use this iterator that it returns to get rid of the rest of the items that we don't need. And here's how we'll do that. First, we want to save the iterator. So we'll say iter equals stdUnique. And I usually try to avoid this keyword auto. I kind of consider it to be lazy coding. But there are some cases where it is quite nice. And I think dealing with iterators is definitely an example of that. It's not too bad for strings, but if you have, for example, an iterator to a map, you might have something like, std map, std string, comma, std pair, int, iterator, or something like this, which is just atrocious. And so in this case, it's quite nice to be able to use this auto keyword, which just infers the type based on the return value of this function. You do have to be careful how you use auto, however. It is possible to introduce some very bad bugs without even realizing it through misuse of the auto keyword. So use with caution. Okay, so now let's erase the duplicate items. And so we'll do that by saying digits.erase, digits or iter, digits.end. So this is going to erase everything from one past the last unique digit all the way to the end of the string, which is exactly what we want. And now down here, instead of iterating over all the possible values of C, we can just iterate over those that appear in digits. Excuse me. Okay, so let's see how that affects our performance. Okay, so that, as you can see, is quite a bit better. We were at almost a third of a second before, now 178 milliseconds, so quite an improvement. But there are a few more optimizations left to be made. And the next one I think we can find by going back to the problem description and considering how our algorithm might deal with this family here. Now this family will not be our solution. It's the smallest, or the 7 prime family that contains the smallest prime. And we're looking for the one with 8 primes, not 7 primes. And so we're going to end up considering this family multiple times as our algorithm executes. First, we'll consider this prime and replacing the zeros. Then we'll consider this prime and replacing the ones. Then we'll consider this prime and replacing the threes. And so you can see that we're doing a lot of duplicate work. Ideally, we would only consider the smallest prime from a particular family because that's the first prime from that family that we will encounter. And it's not so easy to do that, but there is a good heuristic that we can use to avoid doing obviously duplicate work. And that is if we only replace smaller digits with larger digits. That is, for example, replacing 0 with, say, 4 is going to be fine. But if we're replacing 4 with 0, that's either going to give us a number that isn't prime, or it's going to give us a prime that we've already considered, in which case we're looking at the same family that we've already looked at. And so we only need to consider replacing smaller digits with larger digits. One nice side effect of this is it means we can get rid of this whole most significant digit business. Because if we're only replacing smaller digits with larger digits, we're never going to be replacing a non-zero digit with a 0. Okay, so let's apply this. First, as I said, we can get rid of this. Okay, we can get rid of this. And here we just need to say D is going to start at C plus 1, and then also still go up to 9. This is going to completely eliminate this check here. We don't have to check that C is equal to D, and we don't have to check for this most significant digit business either. One thing that should have no effect now, but we can remove it to simplify our code, is this result not equal to n. Because we're now only replacing digits which actually appear in our number, so we know that the resulting number will be different. Okay, I think that should be all we need. Let's go back to our shell and make and solve. And now we're down to 136 milliseconds, continuing to improve. Now, there's one more optimization that I'd like to make before we check to see that our solution is correct. And that comes from thinking about the implications of only replacing smaller digits with larger digits. So if we think about this family here, we can associate each of these primes with the digit that was used to form that prime. So 0, 1, 3, 4, 6, etc. And we know we're looking for an 8 prime family. And that's going to correspond to 8 of the 10 possible digits. And so we can actually conclude that our smallest prime from the family the digit that's being replaced must be a 0, 1, or 2. Why is that? Well, if that wasn't the case, it would have to be one of the other digits. Suppose it was a 3. Well, it can only be replaced by larger digits, so we would have 3, 4, 5, 6, 7, 8, and 9. That's only 7 values, and we need 8. And so we know that r prime is going to have a 0, 1, or 2 as the digit being replaced. Otherwise, it won't be possible to generate enough different values to fill out our family. And so that's the final optimization we're going to make. If we go back here, when we're iterating over the digits of our number, if we find that the digit we're considering is greater than 2, then we're done with that number. We've already considered 0, 1, and 2 if they are present. And so we'll say if c is greater than 2, then we're just going to break. We are done with that number. Okay, so let's go back to our shell one last time and make and time. And we can see we're down to just over 100 milliseconds. Recall that when we started, we were up around a third of a second, so this is quite an improvement. And now I think it's time to check our answer. So let's go back to the archive. I didn't even bother trying to sign in this time, so let's go ahead and do that. Normally I sign in and then it signs me out, and this time I didn't even try. So let's go to the second page now. We're on the second page, and we can see our problem and our answer, and it does in fact match what we expect. So as always, thank you for joining me in this video. Tomorrow we'll be solving problem number 52.